Good evening, ladies and gentlemen. Today I would like to present a review journal paper with the title The Importance of Life Cycle Based Planning in Maintenance and Energy Renovation of Multifamily Buildings. The paper is written by Abul Faz Farahani, Holger Welboom, and Olaf Gallenberg from Department of Architecture and Civil Engineering, Chalmers University of Technology, Gothenburg, Sweden, in the journal Sustainable Cities and Society. Before I continue my presentation, please let me introduce myself. My name is Muhammad Faisal Aryan Sharifin. I am a graduate student in National Union University of Science and Technology, Taiwan. The presentation will conduct based on this outline. First part is introduction, second part is methodology, followed by demonstration the methodology, then continue with the result and discussion, and finally close by summary and conclusion. The paper will be discussed. We can read more detail by click in this link title. If we read the keyword in the article info, there is a four keyword in the article info: energy renovation, energy efficiency, maintenance, and buildings. Each keyword will illustrate that more clearly what is actually the meaning of this title and what will be discussed inside the paper. Starting from the introduction, motivation author to perform this study to lift this issue based on the recent condition of real estate industry sector almost around the world, but more focused in Europe for energy consumed and emission. Total energy consumed by building industry, including the real estate industry, is around 40% of total energy consumed in the world, and the emission contribute and the emission of contribute building industry is around 36% for all total emission come from the other sectors also. Graph of energy performance versus the greenhouse gas emission or GHG is depicted as if the energy performance getting decline, so it will cause GHG emission increasing, and this will bring impact to global warming. Came from this crucial problem in the global building industry sector, we need to find the solution to solve and reduce the impact from this industry. Recent solution for solving this problem is by doing preventive maintenance and renovation building energy perform to get better energy performance, and finally it's reduce the GHG emission. However, there is some barriers in doing building renovation. Number one, renovation processes are complex and uncertain in terms of decision making and planning. It's mentioned by Economidou, Lawson, Rosenfeld, and Steinishek in 2011. Also mentioned by Feminas and Field in 2010, followed by Ryers and Mansfield in 2001, and then the oldest one is Rosenfeld and Sohetz mentioned in 1999. Number two, a lack of knowledge in the renovation process, mentioned by Burnell, Bosch, Lindell, and Molnar in 2014. Burnell, Bosch, Lindell, and Molnar also said the problem is opportunity renovation plan is lack of maintenance plan. The aims of the study present an extension of the maintenance model that already developed by the author Farahani in 2018. This model provides a systematic approach to cost-optimal maintenance and renovation planning by combining the deterioration function of building components with respect to service life costing. Then, in this model will be include energy performance improvement as an optimization criterion, The addition of energy performance improvements includes both marginal investment cost of implementing energy efficiency measures and the reduced cost of operation in the economic evaluation of energy renovation plans. The theoretical framework used in the study is based on the deterioration model proposed in Farahani in 2018. The deterioration model behavior in this model is divided into phases. Phase 1 describes the initial irreversible degradation process, and the second phase describes the phase during which the condition of building component is retrievable by means of maintenance. It's like illustrated in the figure 1 of condition deterioration curve on the top. Minimum accepted condition for each component in this figure is specified 0.2, which determine the end of corresponding estimated service life or ESL. When the condition state below the line of minimum accepted condition is considered reached the failure. And the bottom figure shows the corresponding maintenance in year 15, 30, and 45, and renovation in year 50. In the flowchart, the input variable for each step is placed on the right side square box. This flowchart in the figure to illustrate the modeling process used for the following simulation. The input variable as shown in the figure can be estimated or be taken from available datasets and then calibrated through inspection is put in the right side of the flowchart. Starting with the specified component we want to observe. Follow with the next steps to perform the simulation of the condition and declaration. And also, we want to check the initial service life. Then the next stage is perform the maintenance action and also check the effect of the maintenance. We can adjust if it's not correct. And follow with the next step is estimated service life or ESL, then followed by incorporation of the energy efficiency measure at ESL by doing and watching the obsolescence of the building. And calculation of the energy saving against the reference. Okay, followed by calculation of the EAC value, and the last one is on the constraint of the constraint and the fixed cost. We want to obtain the optimal renovation year. To demonstrate this methodology, the model will apply on three different components as an experiment example. There is facade, roof, and window. In order to demonstrate the methodology in the different component, we can observe the maintenance and renovation data for the given component in Table 1. Table 1 shows the maintenance measure assigned to each component including different operation, maintenance condition, and the respective energy efficiency measures. Since the energy efficiency assessment to be used in the model can be profitable or unprofitable, the given energy saving potential in the following table is considered as the average calculated energy saving possible through the use of the given energy efficiency measures being by Western Book in 2015. In the table 1, we can see component measure for windows. If you want to do the maintenance like repainting outside, will cost 141 Swedish krona per meter square. And we want to adjustment the handles or mounting new ceiling will cost 146 Swedish krona per meter square. And if we want to repainting the inside, we will cost 102 Swedish krona per meter square. And for the replacement, it will cost expensive one. It costs 1,431 Swedish krona per meter square. We should give more attention. The latest maintenance interval for the maintenance is 20,000 a year. For the replacement, we need to do it 30 year. And then the energy efficiency for this will cost 477 Swedish krona per meter square. We will get and saving or the energy potential saving is 12%. And then for the facade, we will maintenance action for the repainting is cost 147 Swedish krona per meter square. With the latest maintenance interval is 25 years. And then for the replacement, it will cost the expensive one 693 Swedish krona per meter square, and the latest maintenance interval is 35 years. And then the energy efficiency will cost 231 Swedish krona per meter square, and we will get potential energy saving is 8%. And then for the roof, the maintenance action for the repainting is need we will cost 175 Swedish krona per meter square with the latest maintenance interval is 20 years. And for the replacement will cost 1,477 Swedish krona per meter square with the latest maintenance interval is 35 years. Energy efficiency will cost 246 Swedish krona per meter square. We will get energy saving potential is 6%. While demonstrate the methodology study will apply assumption for some scenario. The energy first assumption is energy efficiency measure for each component are only for illustration purpose. Second assumption, the corresponding cost based on Halfera Mera study being by Western Block at 2015. And the supporting data of potential energy use reduction are average value also based on Halfera Mera study doing by Western Bjork at 2015. Then the last one, the reference service year in the calculation of energy saving cost is chosen to the longest service life amongst the three components during which technical or performance requirements for each individual components are met. All of these assumptions we can show more detail in table 2. Assumption used in the calculation of energy saving that doing by Westernberg in 2015. The parameter it consists 8 parameters. The one is building energy use. The second one energy saving potential. The third one is energy price. Number 4 is growth rate in energy price. Number 5 is inflation. Number 6 is growth rate in construction and service cost. Number 7 is discount rate. And the number 8 is sharing fixed cost. There will be three scenarios performed in demonstrate the methodology. The three scenarios are considered to perform based on the economic effects of timing in the implementation of energy efficiency measures. First scenario, we will planning in building maintenance under normal induced condition. According to industry standard maintenance and renovation guidelines in Sweden. And the second one, planning building maintenance under normal induced condition, using the proposed method that energy renovation plans are optimized for gradual and deep renovation strategies that proposed from this model. And then the last one, we will apply the deterioration model to a building under worsening in use condition. Summary of the three scenario we can see in the table 3. Scenario 1 will include energy efficiency. It's also applied from scenario 2 and 3. And the renovation strategy, the scenario 1, 2, and 3 also will use the gradual and deep strategy. The building condition, for scenario 1 and scenario 2 will use the normal condition. And the scenario 3, the building condition will use the worsening condition. And for the planning approach, is create differences between the scenario 1, 2, and 3. In the scenario 1, we will use the standard from the Sweden PAU. In the scenario 2, we'll use the cost optimal proposed by this model. Scenario 3 will use the PAU and cost optimal of the planning approach. Result and discussion for the first scenario. In the first scenario, the energy renovation plans are presented for the three components using the industry standard maintenance and replacement interval given by the local guidelines from the SABU 2013. For the gradual energy renovation strategy in this scenario, window and roof are scheduled to be maintained every 15 years, whereas for the facade, the maintenance interval is set for 20 years. And the estimated service life is should attain 50 years for facade and windows and 45 years for the roof. Then the calculation individual and the total cost for the given plan we can see more detail in table 4. In the table 4, the fixed costs are the sharing fixed and the logistic cost and the energy saving are the saving made through energy use reduction. We can see in the table 4. Result from PAU gradual energy renovation plan, as we can read in the left side, are taken from the figure 3 PAU gradual energy renovation plan from the paper. In this presentation, red column will represent the maintenance, black column is renovation, gray column is roof, yellow column is facade, column is windows. Red column and black column is based on the maintenance, what we will do for the action to do renovation. We will do maintenance or renovation. And the gray, yellow, and blue it represent component in the study. Observe. Like we can see in the graph, year 15, we will need to do the maintenance for the roof and the windows. And the year 20, we need to do the maintenance for the facades. And for year 30, we need to do the maintenance for the roof and window. And the year 40, we need to do the maintenance and for the facade. And for year 45, we need to do a maintenance for the all of the three components for the roof, facade, uh, and also for the windows, doing the maintenance and the renovation at the same time. And year 50, we will need to do renovation for facade and so on. Here in this scenario, if the owner decision is to take on a deep renovation approach, since the renovation year for each component is considered to be the year of failure, shortest service life among the components is to be chosen as the renovation year, thus year 45 is to be chosen for deep renovation. In this case, all three components are to be renovated at designated year. We will should pay more attention. The calculated total deep energy renovation cost given in table 5 indicates almost no financial gain in combining renovation measures in the deep renovation strategy as opposed to the gradual renovation. The total of the PAU deep energy renovation plan for the window, the maintenance interval is 15, the renovation year is 45, and will be cost 43 and 43.5 Swedish krona per meter square per year, and so on for the facade and roof. And then the fixed cost is 18 and the saving is 4.5 and the total will be cost 103.5 Swedish krona per meter square. And figure will describe the periodic energy renovation plan. Data table is taken from Figure 4, periodic renovation plan from this paper. Maintenance renovation for window is disappear. The legend for this graph is same with the previous graph. For the year 15, it means we need to do the maintenance for the roof and window. For year 20, we need to do the maintenance for facade. And for year 45, we need to do the renovation for three of the component, the roof, facade, and the window, and so on to year 75. The effect of energy renovation strategy on the life cycle windows. As we can see, if we perform strategic planning, display total life cycle reduction for a single component using both an opportunity and strategic planning in the long-term energy reference planning, the total cost in strategic planning constantly stands lower than the total cost in opportunities planning. Which means if we use the strategic planning, we can save more costs and perform the opportunistic planning. Total, we should pay attention. The total cost for deep energy renovation is 103.5 Swedish krona, and the total cost gradual energy renovation we need more expensive. That is 104 Swedish krona. The result and discussion for the second scenario. In this scenario, the model is used to obtain the cost-optimal energy renovation plans for the respective components. In this plan, the potential combined maintenance and energy renovation years for the three components that result in the lowest total life cycle cost are chosen as the cost-optimal energy renovation plan. The total life cycle cost for each component together with the total fixed cost and energy saving are given more detailed in Table 6. For the windows, maintenance interval is 18 years and the renovation year is 48, with cost 27.5 Swedish krona per meter square a year. And the facade for the maintenance interval is 24 years, renovation is 42 years, and it will cost 15 and 0.5, and so on for the roof. And the total cost for this optimal energy renovation only costs 95.5 Swedish krona. As we can see, it's more cheaper than the previous scenario. And then the plan for cost optimal energy renovation is we can see like in this figure. In the figure, data taken from the figure 6 from the paper. There is only action we need to do year 78 from beginning. In year 18, we need to do the maintenance for the roof and window. And the year 24, we need to do the maintenance for the facade. And the year 36, we need to do the maintenance for the roof and window. And the year 42, we need to do the renovation for the roof and the facade. 48 needs to the renovation for the windows, and so on until year 78. And then the last one, the third scenario. In the first case, in this scenario, it assumes that the induced condition for windows and facade have been worse in time. Due to the changes in the indoor condition, outside environment and tenants' behavior, the window and facade deterioration rates are assessed to have been increased so that the assessed conditions are equal to expected condition in 4 and 5 years respectively. We need to remember the faster deterioration result in will shorter life expectancy, And then the estimation of the life expectancy is possible through inspection toward the end of the service life when the overall condition is low. In the table 7 present in this paper, the maintenance and energy renovation just as well as life cycle costs for the given energy renovation for the BAU energy renovation plan in a building with worsening in use we can see in the table 7. For the windows, the maintenance interval becomes shorter. In year 11, we need to do the maintenance and the renovation in year 37 and will cost 66.5 Swedish krona per meter square. You follow with the facade 15 for the maintenance renovation 37, the cost is 23.5, roof 15 for the maintenance renovation in year 45, and then will cost 29.5 Swedish krona, and the total cost will take 144.5 Swedish krona. It will be more expensive if the duration is going faster. And the renovation plan is taken from the figure 7 from the paper. There is more activity, maintenance, and renovation. You need to do the maintenance faster in year 11 for the windows and do the maintenance faster in year 15 for the roof and facade. Then in year 22, we need to do the maintenance again for the windows and follow the unit year 30 the maintenance for the roof and facade. So on until year 75. There will be more activity to do the maintenance and action if the condition is worse. In the following example, the application of the proposed method in the implementation of the changes in the in-use condition in the deterioration behavior of building components, and so the life expectancy is demonstrated. Considering the faster deterioration of window and facade in this case, the estimated service lives are not shorter, and the total life cycle cost for the two components in table 8 we can see are higher than the cost optimal plan under normal in use in table 6. In the table 8 we can see the windows. The maintenance interval is in year 13, the renovation year in year 38, and it will cost 54.5 Swedish krona per meter square. And the facade, we need to do the maintenance in the maintenance interval in year 16, renovation in year 38 will cost 22.5, and the roof maintenance interval is in year 16, and the renovation in year 44 with the cost is 30 Swedish krona. We take a total cost 126.5 Swedish krona. Compare with the previous condition of the works without using the cost optimal renovation plan. This model for the cost optimal renovation is more cheaper. The PAU model. We can see more detail for the maintenance and renovation in a fig taken for the from the figure 8 in the paper. Just only to do a few maintenance compared with the PAU. Around 11 or 10 activity maintenance and renovation, and not fast compared with the PAU. PAU will do the first maintenance in the year 11 from this model for optimal energy renovation model. We're doing the first maintenance for window is in year 13, follow with the maintenance for the roof in year 16, and then the next interval is in year 36 to the maintenance for windows, and then year 32 maintenance for the roof, and then year 37 to the renovation for the facade and windows. and so on for the next activity until year 76. Summary and conclusion from this paper, we, we can obtain study shown that ignoring the value loss in the economic evaluation of renovation result in an overestimation of the potential gained benefit. Because optimal maintenance or renovation planning result indicate the importance of long-term energy renovation planning as action taken toward the end of component's life expectancy not only limits the optimization opportunities but also result in below standard condition or performance level for the respective building components. The second conclusion that we can take: 38% increase in energy renovation cost due to the changes in the induced condition or the scenario signifies the importance of the induced condition in economic performance of building components. Then the third conclusion, the worsening of the induced condition result is shorter service life, thus higher chance of unexpected failure. These changes, as soon as reported, should be stopped or fixed to avoid further loss of value. Then the last one, the maintenance and energy renovation planning model is quite intensive toward changes in the investment cost and the potential energy use reduction. Therefore, resulting cost optimal energy renovation plans can be used even with uncertain energy investment data. Thank you for listening to this presentation. I hope the review of this paper will be of value benefit for us. See you next time.